Have you ever stopped to wonder where all the water goes when it rains? I mean, really wonder? It falls from the sky, hits the ground, and then... what? Well, that is the super exciting science of hydrology. Hydrology is simply the study of water and how it moves. It's about its journey, on the surface, above in the atmosphere, and deep below in the ground. Think of hydrology like being a detective tracking every water molecule. This science is fantastically important for civil engineers. They need to understand water's path to keep our homes safe, our roads safe, and our cities dry. It's all connected. So why care about tracking water? Because water is powerful. A gentle rain can make a garden grow, but a massive storm can cause a flood that changes everything. Let's follow a single raindrop. Our story begins high up in the atmosphere. Water vapor rises from oceans, lakes, and even plants. As it cools, it condenses into cloud droplets. This is called condensation. When enough droplets clump together, they fall as precipitation, rain. This whole amazing process is the water cycle. It's a continuous loop powered by the sun. Now, our raindrop has landed. What happens next depends entirely on where it landed. In a forest, it might drip to the spongy ground. The soil soaks it up in infiltration. Water can then travel slowly underground, feeding streams and plants. A forest is brilliant at slowing and absorbing water, natural flood prevention. But in a city like Hong Kong, the journey is different. It likely hits hard, non-absorbent surfaces, rooftops, sidewalks, asphalt, so the water has nowhere to go but sideways. This surface flow is runoff, and in cities it happens very quickly. If you're a civil engineer trying to prevent a flood, you need to know exactly how much rain you're dealing with. It's not enough to just say it rained a lot. We need numbers. Engineers measure a storm over time with a rainfall profile or hydrograph. It's a bar chart showing how much rain fell in each time interval. That chart tells the story: steady drizzle or one intense burst. A sharp high peak is often more dangerous than evenly spread rain. That sudden downpour can overwhelm drains. How do we get this data? We use rain gauges. Modern gauges send real-time data to central computers. Engineers can watch the hydrograph form during the storm. Studying past hydrographs reveals regional patterns. In Hong Kong, summer thunderstorms often deliver very heavy rain in a short period. Identifying the peak intensity is the critical moment to design for. The hydrograph turns chaotic weather into a measurable data set. That data is used to design drainage that can stand up to the worst. It's about turning observation into actionable information. Once an engineer knows how much rain is falling, the next question is, how much becomes runoff? That is the water that will flood the streets if it's not controlled. To figure this out, engineers use several tools. One classic method is the rational method. Used for over a century, it's a simple, reliable estimate. The formula looks like this. Q equals C times I times A. Q is peak runoff, I is rainfall intensity, A is area, and C is the runoff coefficient. Q is measured in cubic meters per second, the maximum flow into the drains. I is the peak rainfall intensity from the hydrograph. A is the area we're analyzing, a block or development in square meters. C is the runoff coefficient, a number between 0 and 1 that describes surface type. In a forest or park, C might be 0.1, 0.2. Most water soaks in. In a city with pavement, C can be 0.8, 0.9. Most water runs off. The runoff coefficient accounts for the sponge effect, or the lack of it. Imagine a 10,000 square meters urban site with C equal sign 0.9. Peak intensity, I equal sign 50 mm per hour, which converts to about 0.000014 m per s. Plugging in, Q equal sign 0.9 x 0.000014 x 10,000 equals sign 0.126 cubic meters per s, 126 ls. We followed the journey of a raindrop, measured a storm, and calculated runoff. Why does this matter? Because these calculations are the foundation of flood management, especially in places like Hong Kong, with intense typhoons and heavy rains. If pipes are too small, they'll be overwhelmed and streets will flood. If they're too big, it's wasted money. Hydrology helps get it right. Flooding causes damage, disrupts transport, shuts businesses, and risks lives. By designing robust drainage, engineers are silent heroes protecting cities every storm. But the world is changing. Climate change brings more intense and frequent storms. A 100-year storm may become more common. Planners must rethink designs. Solutions include green roofs, permeable pavements, and urban bioswales, sponge city ideas. and smarter, sensor-driven water management systems help respond in real time. For complex cases, engineers use models like HEC-HMS and local IDF curves. Understanding rainfall and runoff is the first step toward resilient cities. It's an ongoing, critical mission, starting with the science of a single raindrop. If you'd like a detailed calculation for a specific site, ask in the comments. Thanks for watching. Subscribe for more engineering explainers.